Hello, everybody. Today I'm going to read a physics book for university student. That is also my majors at university. Chapter of that book is a book of Serway. Chapter 22 about reflection and refraction of light. You can see the picture. Light is bent as it passes through water with different wavelengths, bending by different amounts. A phenomenon called dispersion, together with reflection. This physical phenomena leads to the creation of rainbow when light passes through small suspended droplets of water. In this chapter, there are totally 7 sections, and today I'm going to read section 1, the natures of light. Light has a dual nature. In some experiments, it acts like particle, while in others, it acts like a wave. In this and the next 2 chapters, we concentrate on the aspects of light that are the best understood through the wave model. First, we discuss the reflection of light at the boundary between 2 media and the refraction or bending of light as it travels from one medium into another. We use this idea to study refraction of light as it passes through lenses and the reflection of light from mirrored surfaces. Finally, we describe how lenses and mirrors can be used to view objects with telescopes and microscopes and how lenses are used in photography. The ability to manipulate light has greatly enhanced our capacity to investigate and understand the natures of the universe. Section number 1 about the natures of light. The question is, what is the natures of light? Until the beginning of the 19th century, light was modeled as a stream of particles emitted by a source that stimulated the sense of sight on entering the eye. The chief architect of the particle theories of light was Sir Isaac Newton. With this theory, he provided simple explanation of some non-experimental facts concerning the natures of light, namely the laws of reflection and refraction. Most scientists accepted Newton's particles theory of light. During Newton's lifetime, however, another theory was proposed. In 1678, Dutch physicist and astronomer Christian Huygens showed that the wave theory of light could also explain the laws of reflection and refraction. The wave theory didn't receive immediately acceptance for several reasons. Firstly, all the waves known at the time, sound, water, and so on, travel through some sort of medium, but light from the sun can travel to the earth through empty space. Further, it was argued that if light was some form of wave, it would bend around obstacles. Hence, we should be able to see around corners. It is known that light does indeed bend around the edge of objects. This phenomenon, known as diffraction of light, is difficult to observe because light waves have such short wavelengths. Even though experimental evidence for diffraction of light were discovered by François Grimidi around 1660, for more than a century, most scientists rejected the wave theory and adhered to Newton's particle theory, probably due to Newton's great reputation as a scientist. The first clear demonstration of the wave natures of light was provided in 1801 by Thomas Young, who showed that under appropriate conditions, light exhibits interference behavior. Light wave emitted by single sources and travel along 2 different paths can arrive at some point and combine and cancel each other by destructive interference. Such behavior couldn't be explained at the time by particle model because scientists couldn't imagine how two or more particles could come together and cancel one another. Here is the image of Christian Huygens. He is a Dutch physicist and astronomer. Huygens is best known for his distribution to the fields of optics and dynamics. To Huygens, light was vibratory motion in the ether, spreading out and producing the sensation of light when impinging on the eye. On the basis of this theory, he deduced the laws of reflection and refraction and explained the phenomenon of double reflection. The most important development in the theories of light was work of Marcel, who predicted in 1865 that light was formed of high-frequency electromagnetic wave. His theories also predicted that these waves should have a speed of 3 times 10 power 8 meter per second, in agreement with the measured value. Although the classical theories of electricity and magnetism explain most known properties of light, some subsequent experiments couldn't be explained by the assumption that lights were a wave. The most striking experiments were photoelectric effects, which we examine more closely in chapter 27, discovered by Higgs. Higgs found that clean metal surfaces emit charge when exposed ultraviolet light. In 1905, Einstein published a paper that formulated the theories of light quanta particles and explained the photoelectric effect. He reached the conclusion that light were composed of corpuscles or discontinuous quanta of energy. These corpuscles or quanta are called photons to emphasize their particle-like nature. According to Einstein's theory, the energy of photon is proportional to the frequencies of the electromagnetic wave associated with it, or E, that means energies, is equal to HF. H here is Planck constant and F frequency, where H is 6.63 times 10 power minus 34 joule is Planck constant. This theory retains some features of both the wave and particle theories of light. As we discussed later, photoelectric effect is the result of energy transfers from single photon to an electron in the metal. This means that the electron interacts with one photon of light as if electron and been struck by a particle. Yet, photon has wave-like characteristic, as implied by the fact that frequencies is used in its definition. In view of this development, light must be regarded as having dual nature, both particle and wave. In some experiments, light acts as a wave, and in others, it acts as a particle. Classical electromagnetic wave theory provides adequate explanation of light propagation and of effects of interference, whereas photoelectric effects and other experiments involving the interaction of light with matter are best explained by assumed light is particle. In the final analysis, is light a wave or particle? The answer is neither and both. Light has a number of physical properties, some associated with wave and others with particles. Thank you very much for your listening. See you next time with the section number 2, reflection and refraction of light. Bye bye for now. See you next time.